So in introducing your work, I think we should start with gravitational waves. Now, like we've just been discussing the celestial objects like black holes and various types of stars, they emit electromagnetic radiation across the spectrum. So X-rays, visible light, radio waves. And each of these sorts of light might tell us something very different about these objects and their interactions with other objects. And I think the general public and my listeners are probably much more familiar with electromagnetic radiation because it's light than they are with gravitational waves, which are fundamentally different. So just what are gravitational waves?
Right. Great question. So gravitational waves are ripples in the fabric of space-time that travel at the speed of light. And so this really goes down to Einstein's theory of gravity, that, gravity is not just some dumb force between two objects with mass, but that it's actually these objects with mass are creating curvature in the fabric of space-time around them. And that curvature is gravity. And so if you have two massive objects that are orbiting each other, they're perturbing the fabric of space-time around them and sending out ripples. And those ripples are very small, but they're measurable. And in fact, the first detection of gravitational waves happened in September 2015, and the announcement came later in 2016. And that was of, two black holes that were roughly 30 times the mass of the sun merging. So these gravitational waves are completely different from light waves. So you call light electromagnetic radiation. That's correct. With gravitational waves, we call it gravitational radiation. So it's a nice analogy. But what really blew my mind when I was starting out studying gravitational waves is that it's a completely different spectrum and it has nothing to do with light, right? So I think naively, when you first think about it, you want to look at the light spectrum where you have, X-rays, optical rays, radio waves, and be like, where do gravitational waves fit on this? It's its own thing. They are not related to each other. And so at the very high frequency end of the gravitational wave spectrum, you have gravitational waves from stellar mass black hole mergers. So black holes that are, between 10 or a few times the mass of the sun to 10 to maybe 100, but that's about it. And those merge in a frequency range that would be in the human audible range. So if our brains had gravitational wave detectors in them and our ears were gravitational wave detectors, when black holes would merge, you would actually hear a whoop sound at the very end of their life. Like you could actually hear it. It's in the human audible band. So those gravitational waves are very high frequency. The experiment that I work on right now is a very low frequency gravitational wave detector. And so whereas the LIGO detector, which made this first detection back in 2015, is sensitive to gravitational waves that are between maybe 100 and 1,000 hertz. My experiment, which is called pulsar timing arrays, the gravitational waves that we look for are 1 to 100 nanohertz. And so to wrap your mind around what a nanohertz is, right? If you're not used to thinking about hertz, maybe it's more intuitive to think about what would be the orbital period of these black holes. Right? So 1 nanohertz is equivalent to an orbital period of 30 years. So these black holes are very slowly moving and they're very widely separated. But importantly, our black holes in this frequency band are supermassive black holes. Those can be 100 million to 1 billion times more massive than the ones in the LIGO band. So we see a different class of black holes than LIGO does. So LIGO could see black holes that are, a few to 100 solar masses, whereas we see black holes that are, 10 million, 100 million to 1 billion times the mass of the sun. So a completely different class of black hole.